This YouTube is about skid mark forensics. The situation is that a car has put its brakes on and locked the brakes relative to the ground, and so um, the view from above, these two lines indicate the boundary of the road, and this is the skid mark. And so let's say that we'd like to know what the initial velocity of the car was at the beginning of the skid marks. If the skid mark was in a straight line with a displacement, a length of 10 meters, and that of course the final velocity is 0 meters per second per second. The assumption here is that mu sub k is equal to 0.2. So first question, why would we use mu sub k rather than mu sub s in this problem? Well, that is because the tire is moving relative to the road, and in that case, one always uses kinetic rather than static friction. Okay, so a side view shows the force diagram, and so let's assume vertical axis up, y, and horizontal axis to the right, which is in the same direction as the initial velocity, which is what we'd like to find. And so a force diagram here shows that there are three forces acting on the car: its weight, the normal force of the road, and a frictional force, which is the kinetic frictional force to the left. You should look at this scenario and realize that the delta v is to the left, and therefore the acceleration is to the left. And by Newton's second law, the acceleration to the left should be pointing in the same direction as the net force to the left, which is the same as the direction for S sub F. So we can do two Newton number two equations here. Newton number 2 in the vertical direction is basically n minus mg is equal to 0. Solving that, we get n equal to mg. Normal force, in other words, is just equal to the weight of the car. And Newton number 2 in the x direction is m times a sub x is equal to F sub F. That's the frictional force, which is mu sub k times n, again because it's kinetic. But n is equal to mg from the previous Newton number 2. And so we get m a sub x is equal to mu sub k times m times g. And we can solve that for a sub x dividing through by m. And I put a minus sign here just to reinforce the fact that the acceleration is in the negative direction. And so a sub x is 0.2 times 10 meters per second using easy numbers. And so a sub x is negative 2 meters per second corresponding to the fact that the a sub x is pointing in the negative x direction. And so now in order to find Vx naught, we can use the third kinematic equation. Because if you write that down, you should realize that we know everything except Vx naught. Vx is 0. A sub x we have just finished calculating, and the delta x is the length of the skid mark, which we're going to assume is 10 meters. And so if we solve for Vx naught squared first, and then take the square root to solve for Vx naught, Vx naught is the square root of 40 meters per second, which is 6.3. Again, just using one calculator, one decimal point on my calculator, and then converting that to miles per hour. 1 meter per second is 2.24 miles per hour, so I can just multiply by this ratio to convert. So that would mean that the car at the beginning of the skid mark, the point at which the wheel became locked relative to the road, is 14.2 miles per hour. And so on the top here, I'm posing a question. Let's say we had the same data except that we had a mu sub k of twice the mu sub k that we assumed here. Mu sub k is equal to 0.4. Simple question: would the initial velocity of the car be larger, or would it be smaller if we worked it out? See if you can do it without doing any math, and then you can actually plug the numbers in and come to the same come to a numerical answer, and then see if you get the same conclusion as you did just thinking conceptually.